Hello, everyone. Welcome to today's talk. So I hope you're all doing well. My name is Amin, and I'm a faculty member in the physics department at Ashoka University. So just a few words about this lecture series before I introduce the speaker and we begin the talk. So Beyond the Classroom is an entirely online lecture series. It helps us take the Ashoka mode of pedagogy literally beyond the classroom and share it with the outside world. In a way, this is a method of making our teaching and research accessible to a broader audience. We think that this is particularly relevant in the present times as the world is engulfed in a devastating pandemic. And each one of us is isolated in our own way, not only physically, but often enough also psychologically and emotionally. Alongside Beyond the Classroom, there are also several other online ventures the university is in the process of developing. Let me mention just one of them. So there is Ashoka X, a newly developing wing of the university, which is devoted to the process of creating and offering full online courses in at least two formats for a wider audience. So for further details about this, please visit the Ashoka X webpage. So let us come to today's Beyond the Classroom talk. So we are very happy to have Professor Manu Awasthi today. Manu is an associate professor of computer science at Ashoka University. His research interests are in the design of high performance and energy efficient computer systems and the use of computing for the common good. Prior to academia, he spent approximately 5 years in industrial research labs. So the title of today's talk is Computer Systems, the Workhorses of the Digital Era. And this talk will provide an overview of the evolution of modern computer systems, go behind the scenes of how they work, and are used to power internet-based services. So with this, let me welcome Manu. Hello, Manu. How are you?
Good, Amin. How are you?
Yeah, doing well. Well, if possible, yeah.
Yeah.
How are things on your side?
Things are okay. Yeah, the same thing that you said, as well as can be expected during a pandemic. So
let us get started with your talk without further ado. And let me just mention that we will take questions at the end. So the audience is welcome to type their questions in the chat box, and we will take as many questions as possible at the end. So the next half an hour is for Manu for his talk. Please start.
All right. Thank you very much, Amin. Let me just share my screen, and if someone can let me know if the slides are visible.
Yes.
And yes. They are full screen?
They are full screen, yes.
Excellent. So given how many different kinds of software we use these days to share our screens, I'm never really sure whether the screen is shared in full screen mode or not. But anyways, thank you for the wonderful introduction, Amin. Happy to be here. What I wanted to do with today's talk was to give everybody a sense of how modern computer systems work to sort of provide the everyday services that we kind of take for granted, the Googles, the Facebooks, the Ubers that we use every day and kind of take for granted, and also give everybody a sense of how things have kind of evolved over time to get to the computer systems that we have today, right? And then I definitely wanted to share the fascination that I have personally with these systems, how they work and how they have evolved over time. Right. So let me just quickly, talk about how computers are everywhere. And I think this is something that almost all of us have realized. By and large, we interact with things that are kind of listed out on the left-hand side of the screen, the laptops, the desktop on an everyday basis to get, our everyday job done. But over time, computers have kind of infiltrated almost every aspect of our lives, and depending on where you are, more so. than if you're somewhere else in the world, right? So for example, if we use things like handheld smartphones, and anything that is of that form factor to consume information, these are essentially computers that are based on the same sort of design principles that our laptops and desktops are based upon, right? And if you look at some of the other things that are kind of listed on this slide, the one thing on the top right here is essentially the inside of a Tesla self-driving car, right? So if you look at one of the Tesla's cars from the outside, it actually looks like an automobile, but the inside, the guts of it is essentially a very, very large scale supercomputer that is taking information from everywhere around it and is making split second, or rather split microsecond decisions to sort of, drive itself and to brake when it needs to if a child or a cow sort of comes on the road, right? Similarly, there are a whole bunch of other kinds of services that people use. For example, virtual reality headsets that some people in the audience might have used. And again, these are essentially compute devices that are, as I said before, are based on the same principles as the laptops and desktops. Right? And these things on the right are essentially what are large scale computers kind of working together that I'll go into details of in just a little bit. Right, so it's kind of goes without saying that computers are everywhere, and they have become even more important in today's world, where we hear about machine learning applications sort of being the panacea for everything. So if you look at a typical machine learning application, what essentially it is at the heart of it is nothing but a model, right? And a model that has been trained with a lot of data that has been gathered over time, and different kinds of data that has been gathered, depending on the kind of model that you want to train. Right. So for example, if you want to train a model that tells you whether a picture is of a cat or a dog, then you have to feed that model lots of pictures of cats. Right. So to be able to train this model, what it has to do, it has to take in all this information and kind of train itself so that it can recognize the next picture that you feed it as a cat or a dog. And what that essentially means is that there is a lot of compute that has to happen behind the scenes so as to be able to create this model. And again, this is a very simple cat dog model that I sort of described right here, but a lot of modern day applications, especially the kind of things that go into your recommender systems, for example on your amazon.com webpage, are essentially machine learning applications, right? So what I sort of want to emphasize over here is that all of these things that we use on an everyday basis are powered by massive amounts of compute that are carried out by modern day computer systems. Right. So if you look at a typical computer, from the outside, we see, a desktop looks like something like this, a laptop has a form factor like this. And if you look at a smartphone, it is something that fits in the palm of your hand. And it is easy to think that these all of these are sort of different kinds of machines. But if you abstract everything or all the details out of all of these machines, what ends up happening is all of these modern day computers are built up of three major components, right? One of them is the brains of the machine, which is the CPU over here. The other one is this component over here, which is known as the memory. And the third one, which is shown at the bottom right, is essentially your storage device or your hard disk, right? So at the heart of it, most modern day computer systems that we encounter are essentially made up of some combination of these three major components, right? So how did we get here? Let me just quickly dive into a bit of history about computer systems. How did we get to where we are today in terms of desktops, in terms of laptops, in terms of smartphones? When computers started out, they were not really digital like we are used to seeing them today. They started out as mechanical, then they became electromechanical, then they became digital. And the earliest computers, which was essentially this one that I'm showing on the left, which is the ENIAC circa 1945, was essentially the size of an entire room, right? So and Compared to today's standards, this is a pretty rudimentary computer, right? I mean, it really couldn't do much, but it was the best of the best for the times over there. But as I said before, the way it's going right now is that the the smartphone that you carry in your pocket every day is multiple orders of magnitude faster than the computer, the set of supercomputers that put man on the moon, right? So we started out from computers that were size of a room, and now we have this massive compute capacity that sort of fits in the palm of our hand, right? So the question is, how did all of this start, right? I mean, why did we start to need computers in the first place? And the answer to that question is rather not very obvious, right? And let me just tell you a very quick story as to why the need for computers started. So imagine the year is 1939, the World War II is kind of going on, and at this point in time, Germany is kind of winning, right? They have a superior everything, and they are able to mount attacks on the Allied forces and kind of get away with it. And the Allied forces have no sense of where they're going to attack next, because what the Germans are doing is essentially securing their communications using this device, which was known as the Enigma machine at the time, right? And because they were able to do secure communication, the Allies were not able to decrypt what was happening and what they were talking about between different posts. For example, they had no idea where or when the next attack was coming, and as a result of that, the Allied forces were kind of losing the war to some extent, right? So one of the reasons why people wanted to create machines or create compute machines was to make sure that they were able to sort of take these messages that the Germans were sort of, or take these encrypted messages that the Germans were passing back and forth between themselves, and decrypt them to some extent, right? And imagine this was the era before computers, so any decryption of what essentially looked like gibberish was being done by humans using pen and paper, and that was, of course, not very efficient, right? So what the Allied guys wanted to do was essentially win this war, and one of the ways they figured out was if they could break the German communication codes, they would know when the next attack is coming, and they would probably have an upper hand in this war, right? So what they did was, again, as people do in most of these scenarios, is they picked up a bunch of very smart people and put them together in a nice surrounding north of England. So this is Bletchley Park, a very nice manor north of England, where they put this person, who is the father of modern computer science, Alan Turing, and a bunch of other smart people over there. And they were tasked with the job of, taking the encrypted information that they had snooped on, the Allied had snooped on, and sort of converting them into something that was plain text and that made more sense, right? And what these guys sort of came up with, the team at Bletchley Park came up with, was the first version of the electromechanical computer, which was designed to break the codes that the Enigma machine had created, right? So you had these encrypted texts, and given some more information about what regular words or more commonly used words mapped to, they came up with this first computer, which was again a very special purpose computer, right? The idea there was that it wouldn't be able to run any program that you gave it, but it was very good at breaking codes that the Enigma machine had created, and these things were essentially what were known as the Bletchley bombs, right? So that was the genesis of the first computer, which was essentially the mankind's wish to win a war, and sort of do the kind of computations that were needed to be done, which at that time were not feasible because of the limitations of the human condition, essentially, right? So when the first prototype computers were created, then people sort of wanted to build upon that, right? I mean, as I said, this was a very special purpose computer that people had built. Now, what people wanted to do was to build general purpose computers, right? I mean, I want to build a machine that is going to be able to run any program that I want. And one of the first steps in that direction was taken by this person called John von Neumann, who was a mathematician and again a computer scientist from Hungary. And among his many, many contributions, one of the things that he proposed was a model for creating general purpose computer systems, right? His contribution was so pervasive to some extent, right? That every version of the machines that I had, or the compute machines that I had shown on the previous slide, are essentially some derivation of the model that was proposed by John von Neumann, right? So what was this model? What he said was essentially, if you want to create a general purpose computer, you at least need to have two components in there, right? One is essentially the brain, which is the processor over here, which again relates to this CPU cartoon that I had early on. And then the other thing that you need to have is a memory, and this relates to this memory component that I had seen over there, or I had put over there in one of the previous slides, right? And his idea was relatively simple, right? I mean, if you want to run a program is nothing but a sequence of instructions, and these sequence of instructions have to be operated on some data. At the start or during the run of the program, these sequence of instructions as well as the data that they need to operate on are stored in memory, right? But the memory itself can't do any computations. It doesn't know what these instructions mean. So in order to make sense of these instructions and to do your additions, multiplications, or divisions, or whatever it is that you want to do, you have to bring all of these things over to the processor. The processor has the capability and the circuitry to be able to, figure out what you want your program to do along with the data. You bring it over, you do your math over here, and then once you are done, you send the results of your or your program back to the memory. So this was sort of like a general model that he had proposed, right? So models are nice, right? I mean, but in order to have something workable, you want to take that model and convert that into something which is more feasible engineering wise. So what was to be potentially done was to take these models and convert these processors and these memories into something which was more tangible, right? I mean, you needed a memory that could store your information, your instructions, your data, and you need a processor that could do your additions, the multiplications, and the divisions, right? And how do you do that? And one of the ways that very smart people over the course of time figured out was inventing this device called the transistor. The transistor is nothing but an on-off switch, but if you take a bunch of these transistors, you can create what are known as logic gates from them, right? And then you take a bunch of these logic gates and connect them together, you can create a very sophisticated circuit that is able to carry out any kinds of operations that you want, including your additions, multiplications, and divisions, right? And again, this was one of the very seminal contributions to the field of computing by these three gentlemen over here, who were awarded the Nobel Prize in, I think, physics in 1956 for the invention of the transistor, right? So now we have a model of how computers can function. We have the basic building blocks, which are the transistors, which can then be combined together to build each one of these components that we have kind of talked about. Right. So now let's say I'm able to somehow combine each one of these things, and I'm able to come up with a general purpose computer. So I have transistors at the very bottom, and then I have computers at or I have compute circuitry at the very top, right? Now somehow I have to tell them what to do, right? I mean, the computer is capable of doing an addition, but I have to tell it to do an addition, right? So how do I communicate with the computer? This again, we have come a long way about how we used to communicate with computers over time. This is the Harvard Mark I, again a World War II electromechanical computer, right? And the way we used to communicate with this computer was using these rudimentary devices, which is essentially just punch cards, right? So if you wanted to write a program, you had to think about sort of converting that into an equivalent of Morse code, dots and dashes that you can see over here, and then sort of type out your entire program as dots and dashes on this piece of tape, which was then fed to the computer, and the computer interpreted the sequence of dots and dashes as additions, multiplications, divisions, whatever it is that you had willed the computer to do. Right, so so this is how we started sort of writing the first kind of programs that we wanted to write. But over time, we figured out, I mean, we as humans are not really, created to think in terms of dots and dashes. We sort of tend to think more in terms of natural language, right? So we wanted something that was more closer to natural language to sort of tell the computer what to do. And that kind of led to the rise of these plethora of programming languages that you have available today. You have your C, your C++, your Java, your JavaScript, so on and so forth. Right, so you have all these languages, and the primary purpose of these programming languages is to take whatever ideas that you have in your head or your algorithms that you have in your head, and to be able to write them in a fashion that is as close to the English language or as close to the native language that you're used to thinking in, which can then eventually be sort of interpreted by the programmer and convert, or rather the computer, and converted into the language of the computer, right? So what I didn't mention up until now, that each one of these CPUs that we have talked about has their own language, which is very, very different from what we have in terms of humans, right? So let's say I want to build a rudimentary computer, and I say, well, okay, this should be capable of doing additions, multiplications, divisions, so on and so forth. And I keep adding those items to the list of things that the computer understands, and that sort of adds to the vocabulary of the computer. And because of the model that it follows, which is, programs or instructions and data have to be stored in memory, of course the vocabulary has to include things that need information to be moved to and from memory to the CPU, right? So people create these languages for the computer, and then another set of people created these languages that are the programming languages. We as humans were able to better express what we wanted the computer to do in terms of these languages, these programming languages that were created. But then again, it had to be converted into this sequence of zeros and ones that was something that the computer could understand. And these sequence of zeros and ones were essentially instructions that were derived from the vocabulary of the computer, right? And this was a job that needed to be done, right? So I have to take this piece of code that I have written my algorithm in and convert that into the language of the computer, right? So how do you go about doing that? And that led to the evolution of yet another piece of very sort of complex software systems that run on top of your hardware, but below your applications, right? So if you want to think of this, you can think of this as a 3-layer cake, where you have your hardware at the very heart of it, right? So you have your CPU that is capable of running any instructions that you want it to run. And then whatever algorithm that you want to, or whatever problem that you want to solve, you can write the solution for that problem in a language that is very close to, let's say, English, in this topmost layer of the cake, right? And then this middle layer of the cake, which is the system software, which comprises of your operating system, which comprises of your things called compilers and language runtimes. What they essentially do is bridge this gap, right? I mean, so you're able to take the application that was written in a higher level programming language and convert that into the language of the computer, which is derived from this vocabulary of very simple things like adds, multiplies, and divides that the computer can actually understand, right? And so behind the scenes, there is a whole bunch of this translation that is happening every time you run something as simple as a browser. So, when you double click on a browser or your word processor, all of these different components of the cake, of this 3-layer cake, essentially come or are involved in the execution of the application that you are currently running, right? So now that we have a broad framework in terms of how computers work, right? Or rather, at least how they are organized, or rather how computer systems are organized, where you have your hardware at the very middle, then your operating systems and your compilers in the layer above it, and then applications on the very top of it, which are essentially written in programming languages of the contemporary day. right? So now let's take a look in terms of how what we have talked about so far, or the framework that we have developed so far, can essentially be used for sort of developing the services that we sort of use every day, your Google, your Facebook, your Amazon, your Uber, so on and so forth, right? And again, each one of these are individual implementations in their own right, but if you abstract out a whole bunch of things, at the end of it, they are doing a lot of things in a very similar fashion, right? And I'll take the next 10 or 15 minutes or so to sort of give you a sense of what is happening over there, right? So for example, what happens is what happens in the case of when you have opened up a browser and then you have opened up google.com, and then you sort of write in a search query, and almost instantaneously it gives you a bunch of results that are kind of displayed in your browser as well, right? So if you look at this number over here, 0.71 seconds was the amount of time that this query, or the results of this query, were sent back to the user. And that's essentially fascinating, right? So before I go into the details of how this works, let me give you a little bit of a background on how information is sent back to you when you type something in your browser, right? So here you are the user, you are using some browser somewhere, and you open up, let's say, a website. What happens is that information, whatever website and information that you wanted to access, is kind of encoded into packets of bits, and then they are routed over probably halfway across the world to, let's say, a server that is sitting in North America, or a server of google.com, let's say, that is sitting in North America, that has the information that you're looking for, right? I mean, you're looking for this web page, and it essentially is sitting there on the storage device of some computer in North America, and then it looks up its storage device and figures out, well, hey, I have the data that you're looking for, and let me send it back to you. So I'm going to encode it again in some bits, and packets are routed again back all the way to your computer, and this is where you sort of see the information on the screen, right? So again, there's a lot of processes that are sort of involved here in, let's say, getting back a very simple web page worth of information to you. Now, let's say you are doing a Google search, which is essentially trying to give you information about the entire world of information that sits out there, right? So if you look at this, there are, at the time when this screenshot was taken, let's say 6 months back, there are 130 trillion individual pages that were there on the internet. And what you're asking one computer in this case to do is look up information that might be sitting across any one of these 130 trillion pages and send it back to you in 0.71 seconds. And I mean, that seems like a Herculean task for one simple computer to do. And that is where you have to sort of, gather the help of more computers, right? So I don't know if anyone of you have seen this movie, the Clone Wars, but there is an entire army of soldiers that are essentially exactly the same, right? So over here, you see there's an entire army, and each one of these soldiers looks exactly the same. And similarly, when it comes to getting information back from that could be sitting anywhere in one of those 30 trillion or 130 trillion pages of information, what you essentially do is you sort of ramp your computational capacity up from one computer to, let's say, multiples and multiples and multiples of computers. And then you sort of go to the right computer that has, the right information that you're looking for, and get it back, or send it back to the user, right? So this is where you when you start having these large number of computers that are kind of working together, you almost create a warehouse full of computers. And I'm not even making this up. There are a lot of these installations. If you see this picture on the left, it is a picture or an aerial shot of what is known as a data center, right? And if you go inside the data center, what you'll see is these aisles, and each one of these very, very long aisles is essentially made up of these columns, which are known as racks. And each one of these individual sort of rows on the rack or the column that you see is one computer, Right? And this is just one aisle. So you can see that there are, so many different computers in just one aisle, which are sort of interconnected together. And then you have multiples of these aisles that are sitting within a data center. And then you have multiples of these data centers that are sitting across the world for just one company, let's say the Google or the Facebook or Twitter or whichever one have you. Right. So now you can see that the information that we are getting back from a simple search query that we had typed in our browser might be going to a number of these machines where some small portion of these 130 trillion pages of information that Google has collected over time is actually, searched to see if that information matches the query that you had sent over to Google to give you the results of. And all of these results are kind of combined together to send back to you the result that you were looking for in such a very small amount of time, right? And again, I'm missing out on a whole lot of details regarding how this works, but hopefully it gives you a good sense of how all of these individual computers or individual machines can come together to do something which was almost computationally intractable for just one simple computer, right? All right. So this is essentially what I was, this is a more sort of a visual representation of what I was talking about. So here you are typing the results of some query that you want answers for. This information is again encoded, traverses a bunch of wires over what we today known as the internet, goes into the Google's data center, and where it is kind of distributed across a bunch of these different machines. Each one of these different sets of machines work in tandem to sort of look for the information that you have requested. And maybe one of these machines will actually find the information that you have and send it back to you. And because you have so many machines working in parallel is the reason why you are able to sort of get the data that you requested in such a small amount of time, right? So one thing that I also wanted to mention was it's not just the fact that you have to work with large amounts of data for a single Google query, let's say, but even if you are looking at a web page, whatever happens when you go to your homepage on facebook.com, again, I wouldn't know, I don't have Facebook, but then you would see, there is this timeline stuff that is there, and then you have these shortcuts, you have a bunch of these settings, you have your chat, there are probably ads being shown to you. There is a recommendation about friends that might be there. And all of these different things are essentially different sort of software services. And just to render what it seems like a simple web page, all of these software services, which potentially might be running on different servers in, let's say, Facebook's data center, have to come together to render this web page in a very short amount of time, right? So again, there's this parallelism or this division of work that needs to be done across multiple machines that I had talked about earlier, comes into play in devising everyday services that we use. Right? So, okay, this is all nice and good, right? I mean, because we are able to distribute our work across a bunch of many machines, we are able to get our work done very, very quickly, and we are able to see these web pages render very fast. We are able to see the results of our Google queries come back to us very, very quickly. But as you can imagine, nothing is free in the world. Right, so you have these massive installations, these massive warehouses that have hundreds and probably tens of thousands of servers that are sort of running all the time, waiting for requests of users from everywhere across the world kind of come in, right? And as you can imagine, none of this is free. Why it's not free? First, I mean, of course, you have to put in a lot of money to sort of create these installations. I mean, these are brick and mortar installations. So that's point one. But then again, you have to sort of put in the servers that are running 24/7. Each one of these servers or these computers that we have today are comprised of a bunch of different components like we had talked about. So you have your CPUs, you have your memory, you have your storage devices, and all of them are running all the time, which are essentially consuming electricity. Each one of these machines are kind of interconnected to each other. So you have what are known as network switches and routers that have to be provisioned so that each one of these machines can communicate to each other, right? And now once you have tens of thousands of machines sitting in a closed space and are sort of running all the time, they tend to produce a lot of heat, right? And if they're producing a lot of heat, then you have to provision this facility with the right amount of air conditioning as well, so that your machines don't go down, and in the middle of the night, you're not able to do your Google searches anymore. So there's a lot of air conditioning that has to be provisioned in each one of these data centers, right? And all the things that I have mentioned so far are the ones that consume electricity, right? Now, this has implications for a bunch of many things. First is essentially, of course, there is a lot of money that has to be spent on the power bill. So that's point one. But these are big companies, they generate a lot of revenue, so they can afford the power bill. What I really wanted to talk about was what were the implications of these very large installations that consume a lot of electricity on the planet that we live in, right? So if you look at the scale of electricity consumption, this is 20,000 kilowatt or terawatt hours is essentially what the electricity demand of the entire world is. 1% of that, which is 200 terawatt hours, is what is used by the data centers of the world, right? So 1%, and this is relatively recent. I think this is from 2018. And if you look at this graph on the right, what this shows you is a projection of how this electricity consumption is slated to increase. So this area under the graph for the yellow part, or rather the green part, is the one that is the energy consumption of the data centers. The x-axis over here is year, which is increasing from left to right. And you can see that the electricity consumption of these data centers is projected to increase sort of exponentially over the next 10 years or so. And again, these are projections, so I don't know whether or not they will come true. But then again, it's food for thought in terms of the fact that these installations consume a lot of energy, and it befalls upon us to kind of design computer systems that are energy efficient, so that they don't sort of keep adding to this problem of climate change that we are facing, right? Because again, the energy that is powering each one of these data centers, we don't, or at least I, at this point in time, I'm not entirely certain whether this is actually green energy or that is coming from non-renewable sources like coal or gas or something of that sort, right? So with that thought, let me just quickly close here. What I really wanted you guys to sort of take away from this talk, if you don't take away anything else, is essentially the fact that these things that we use every day and kind of take for granted are essentially very complex and continuously evolving systems, and they have both a software and a hardware component to it, right? And over time, over time, the acceleration in terms of how these things have evolved has increased very, very quickly. And one of the things that we should sort of think about is making sure that we have some, idea about the energy implications of all of these services that we are using every day. Every email that you send, every Google search that you do, every time you go and open up Twitter or Facebook, essentially has an energy implication. And that is something that let's say we should not forget, right? So with that, let me just quickly close here, and I'll pass the baton back to Amin to take it forward from here.
Thank you very much, Manu, for a very interesting talk. So we move on to the Q&A session. So I have a few questions of my own, but let me just say that if there are any questions from the audience, please use the Q&A feature to ask your questions, and then I'll direct them to Manu. So yes, Manu, so one question I had was, you had mentioned earlier in your talk about the von Neumann model for modern computer systems. So I'm not very familiar with the subject and the history here, but I was just curious as to, were there, so I know that this, I guess, builds on earlier ideas of Turing, right? So were there any competing ideas or alternatives to this von Neumann architecture which were considered or seriously considered? I mean, I'm guessing that this must have been the best idea, of course, that's why it was taken up. But in that period, were there other ideas about what computer architecture might be like, which were considered?
Right, that's a good question. I don't know if I have a good answer to that. But let me take up your point about the von Neumann architecture being the best idea, right? So I don't know if it was the best idea, or at least it was the best suited idea for that era of time. And this was the kind of computational model that people could get behind and start implementing to some extent. What we have figured out, and again, it took a life of its own. Every new architecture that kind of came into being essentially followed the von Neumann architecture as well. And over the course of the last 70 odd years, what we have figured out is that for the kind of applications that we have today, the von Neumann architecture does not or is not the best model anymore. Right. So the idea for the model is that you have two separate components. You have your processor, you have your memory, and things keep moving back and forth between these two components. Essentially, the communication highway between the two has now become a bottleneck just because of the tremendous amount of information that we are dealing with.
Yes. Interesting. Thank you. So the other question was about the later part of your talk, where you mentioned, where you talked about warehouse scale computers. So again, I was curious, that given the rate that data is generated today, and also if you look over a period of time, the exponential growth in how much data is generated and which needs to be stored, is it really realistic and feasible that we can go on like this? I mean, just like building bigger and bigger warehouses, and also, I mean, there is, I guess, probably a distinction to be made between, I mean, not all data is probably, although it seems all of it is stored, but probably not all of it is equally important. But so I was just wondering that, given you also mentioned the impact on, like how much energy you use up and so on. But I was just wondering what I'm sure people are thinking about this already, and how this goes forward, basically.
No, that's an excellent point. So and you're absolutely right. The rate at which we're generating data is, for the lack of a better word, ridiculous. And you're also very right that not all of this data is actually useful. But what we have come to at this point in time is that storing information is also very cheap. Right? I mean, if you look at the typical cost of storage per bit or dollar per bit, it has fallen down drastically in the last 20 or 30 years. So what has happened is, although a lot of data is being generated, because storing it is so cheap, people are very afraid to, or people are not willing to throw any data away. Right? Because the idea is that I don't know how this is useful right now, but I might find a way to make this useful at some point in time in the future, right? And at that point in time, it would be terrible if I threw away my data. So from the data storage perspective, I think I think we just go to see people piling, or rather hoarding data, and at some point in time, some people might figure out that, okay, this is not worth it, and then we'll start discarding data at some point in time. But to your question about whether these installations are going to grow, I think at least in the near future, they definitely are. Because what is going to happen is a lot or a larger fraction of the world is going to be connected to the internet. It only used to be the West, the Americas and the Europe that were connected to the internet for the largest portion of the internet that has been alive. But now, because of cheap data rates in Africa, Asia, a lot more people are getting connected to the internet. And then people who are living there or people living in Asia are also demanding better quality of service, right? So you can't take a request that is generated in India and sort of send it all the way to North America for you to get your results back, because it just takes forever to do that. Right, so you'll have to put some more data centers, somewhere in the subcontinent, and I'm pretty sure at least in the near future, things are going to keep on growing. How sustainable that is I don't really know.
Interesting. Thank you. So let us go over to the questions we have from the audience. So, by the way, you're all encouraged to type your questions. There are other questions. So, okay, there's a quick question from Chavi. So Chavi is asking, okay, which movie did you just mention? There was this slide you had where you had these robots. So which movie was that?
It was the Clone Wars, I think. Star Wars Clone Wars. Okay. Well, I just Googled for Clone Wars, and that was the image that I found. So, yeah.
Then there is an anonymous participant asking for book recommendations for beginners, which is learner friendly. So yeah, I guess related to the topic of your talk. So do you have any book recommendations?
Book recommendations in terms of general reading, or book recommendations in terms of textbooks?
Well, no, I guess, okay. The question says kindly recommend some, yeah, the comment says kindly recommend some book for beginners, which is learner friendly.
Huh. So there was this one book, let me see if I can find it. I think The Soul of the New Machine. If I'm not butchering the name, and that is essentially an excellent sort of introduction in terms of getting behind the scenes in terms of how computer or rather CPUs are designed, right? So think about the process of creating a CPU and dramatizing that to be a spy movie to some extent, right? I mean, you start reading that and you won't be able to put that down.
Okay.
I'd recommend everybody to read that book.
Good. So the next question is, what are clouds or cloud computing?
Good question. The definition depends on who you are asking, but I'm just going to go with what we call sort of public clouds today. So again, at the heart of it, if I really want to sort of make things super abstract, a cloud is nothing but a collection of computers that have been connected together in some way, right? So think about, or if I could go back to that warehouse scale computer, or one aisle in the warehouse scale computer that I had sort of shown, then it's just a bunch of servers connected together. And now your servers connected together could potentially be providing you all different kinds of services, right? So your cloud could potentially be providing you hosting services for hosting your websites. It could potentially be providing you storage services, think Google Drive or a Dropbox for that matter, right? It could be providing you a portion of the machine so that you can, sort of have a computer in the cloud, so to say. So when you talk about, creating AWS instances or Google Cloud instances, what that essentially is doing is taking one of these physical machines that is sitting in a rack somewhere and using, again, this sort of middle layer software that I had talked about before, or system software, to create a private chunk of that physical machine, that is available just for your use, right? And there are 4 other people from other parts of the world that have small private chunks of machines that they can use for their own. So at the heart of it, clouds are nothing but, a bunch of machines connected together.
So there's one more question. Yes, which is from Stanton Nobu. Yeah, which is, I guess it relates to the machine learning part, which you mentioned, and it's about how these, like Facebook and YouTube, how basically have a premonition as to what you want to see next. So the question is, how do Facebook and YouTube know what exactly I want to see or watch, as they already put on the screen before I go searching for it? So,
Right.
yeah.
So again, they are basically tracking everything that you're doing, right? So they have these, once you log into your account, they are essentially tracking or if you go to YouTube, they're tracking every click that you did, every video that you watched, and they have been tracking it ever since you created that account that you have been using, right? So again, sorry to be sounding very dystopian, but that's how these models work. So over a period of time, they have collected a bunch of data about what your preferences are in terms of the kind of videos that you watch, right? And then they have trained a model to sort of predict the kind of videos you might like, right? So they took this data of videos that you have already watched, the history of that, fed that into a model, and this model is now trained to recommend videos specifically for you, the user, right? And for each one of these, millions of users that they have, they might potentially have a model that is recommending videos for each one of these people, right? So they know who you are because you log into the website using some credentials. They know what you have watched in the past because they're tracking every click that you did, and from that point onwards it becomes, quote unquote, relatively simple to create a model and create recommendations, and then they can have these recommendations created beforehand, right? So let's say you went in today, and they ran the model and created a bunch of recommendations, stored it. Once you logged in tomorrow, they just showed you those recommendations right away.
All right. So I don't see any further questions. Maybe yeah, let me, if anyone has any questions, please ask at this point. Otherwise, we are close to the end of the session now. Let me just check once more. Okay, there seem to be no further questions. So it only remains to thank you, Manu, for this very interesting talk. And I would like to thank also all of the participants for joining in. So, okay, so that's all we have. Thank you very much. Take care.
All right, thank you and good night, everyone.